Alright guys, welcome to our Unit 13 and 14 summary sheet. I'm going to preface this will be a long video because I'm combining two units together. Unit 13 being probability and Unit 14 being statistics. Let's get to it. So starting with Unit 13, talking about categorical data. We talked about displaying information in two-way tables, and this is categorical because people are fitting nicely into categories. If I want to ask how many total people are surveyed, that's just coming from this number down here in the lower right of your table. So that would be 240 people. The probability of selecting a male would be 60 out of 240. Probability of selecting somebody who drives an SUV would be 156 out of 240. Now, when I say what's the frequency of females who drive an SUV, I go to my table, females who drive SUVs, and I see there's 135 of them. Now, I'm not asking for a probability, I'm asking how many are there. So notice how I'm not writing that as a fraction divided by the total. What is the probability of drivers that drive a sports car given they are male? So this is where I go to given they are male. That's that row. So there's 60 males in this study. Then that they drive a sports car. 39 males drive sports cars. And that would be your probability. Now, notice how everything that I did for the probabilities was in a fraction. Probabilities are technically fractions, decimals, or percents. Now, on the Regents, if we ask you for an exact probability, your best bet is to leave it as a fraction, and that's usually what they're looking for on the exam. If you write it as a decimal, but you round that decimal, now that decimal is no longer exact. Same thing with percents. So I just like to tell my students that exact probability means just leave it as a fraction. Next is Venn diagrams. So I should be able to give you a Venn diagram and have you interpret how to read it. And you could even come up with a two-way table based on the Venn diagram if you're comfortable with that. So if I want to find out how many total people are surveyed, I am just going to add all these numbers together. So grab my calculator, 239 plus 81 plus 324 plus 956. And I think it's 1600, and it is. Don't worry, I didn't add that in my head. I've just done this Venn diagram plenty of times. All right, so there are 1,600 people in this study. Now, keep in mind, the 81 are the people who are in Algebra 2, and they're a sophomore. That's why they're in the overlap of the circles. So when I say how many students are enrolled in Algebra 2 and a sophomore, that's just 81. Probability of selecting a student in Algebra 2 but not a sophomore. Okay, so I go to my Algebra 2 circle. So everybody in the circle is in Algebra 2, but I don't want to overlap with the sophomore circle because it doesn't want my student to be a sophomore. So therefore, that's 239 total students. Now, since it's asking for a probability, that means out of everybody in the survey here, so that would be 1,600. Now, again, if you wanted to put this into a two-way table, let me zoom in real quick, because I know some people hate Venn diagrams, and that's okay. 1, 2, 3, 1, 2, 3. You could quickly do a little A2, not A2, sophomore, not sophomore two-way table, and keep in mind that everything will add to 1,600 because that's your total number of students. There's 81 students in both. For Algebra 2, there is 232 in Algebra 2, but not a sophomore, so I think I might have missaid the number, so 239 is what I meant to say. There are 324 sophomores that are not in Algebra 2. And then from there, you guys would have enough information to fill out the rest of the two-way table, to fill out the totals, and this neither. Oh, actually, wait, I know the neither. It's 956. Perfect. All the numbers to help you figure out the margins. So I'll leave that for you if you want to tackle that. All right, just trying to adjust my thingy here. Okay, so next is just a quick little notation reminder. I apologize for moving this thing around, so there we go. First thing, this means not, this means and, this means or, and blah, 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 blah. This is your or formula, so keep that in mind as well. And then your last symbol, this means given, and its formula is the and divided by whatever is given. So notice how it's given B, that's why it matches in the denominator. Okay. So let's get to it. At Williamsville East, the probability that students are involved in a club is 0.64, and the probability that students are involved in a sport is 0.55. The probability students are involved in both a sport and a club is 0.43. Let C represent involved in a club and S represent involved in sports, and find each of the following. So the first thing they're asking me is the probability of not being in a club. Well, if being in a club is 0.64, then not club would be 1 minus that, which would be 0.36. This is asking for the and, which they actually told you. Club and sport is 0.43. Now, using my conditional rule, I know probability of club and sport is equivalent to probability of club, or I'm sorry, I might have said that wrong. Probability of club given sport is equal to probability of club and sport divided by probability of sport, because again, whatever's given goes in the denominator. I know that the and is 0.43, and the S for sports is 0.55. So that would be 43 over 55 if I reduced it by getting rid of the decimal. On a Regents, they'd probably give you some sort of rounding direction there, but for the moment, I'll just leave it like that. Now, lastly, your OR formula. This is the probability of club plus the probability of sport minus the probability of club and sport, because you don't want to count those people twice if they're involved in both. So probability of being in a club is 0.64. Probability of being in a sport is 0.55, and then the and was 0.43. I'm going to go to my calculator. So I'm just going to do this in terms of integers to help me out here. 64 plus 55 minus 43 would be, so 0.76 in terms of our decimals, would be the probability of being in sports or a club. All right, moving on to the next page, independence. This is always asked on the Regents, so I'm going to put a nice little star here. Hopefully this doesn't make me a liar, but I'm pretty certain it's always on the exam, like 99% certain. The big idea with probability is that you're going to compare the probability of A and then the probability of A given B for events A and B. And if they are equal, they are independent. If they are not equal, they are not independent. So I always think not equal, not independent. And just make sure you label your work. Otherwise, you're honestly going to forget what you're even computing. So if I want to figure out if being male is independent from driving an SUV, I would figure out the probability of male and then the probability of male given SUV. So probability of being male was 60 out of 240. Probability of male given SUV, so given SUV, male, that's 21 out of 156. And then I grab my calculator. 60 divided by 240 would give me 0.25. 21 divided by 156 is 0.134, we'll say. Dot, dot, dot. Because these are not equal, the events are not independent. You are actually less likely to be a male given that your person drives an SUV. If I got equal decimals, though, then I would say the events are independent. All right, next is talking about our AND rule, which AND implies we're going to do some multiplication. So if we know we have independent events, we can just simply multiply them together. If we have not independent events, we're still going to multiply, but we're going to have to be cautious of how that second probability is impacted. So this just means the probability of event B happening is adjusted because event A happened first. So let's practice this. You have a drawer full of 8 black socks and 4 white socks. Without looking, what is the probability you pick out a white sock, put it back, and then pick out a black sock? So first of all, I think it might be nice even just to draw a visual here. You have 8 black socks. So 1, 2, 3, 4, 5, 6, 7, 8. And then you have 4 white socks. So I will do green for white. Okay. You have 12 total socks then. So that first selection of getting a white sock would be 4 out of your total of 12. Now, you put the sock back, so you got to envision, okay, so how many socks do you have in the drawer then? 12 again. Now, if you pick out a black sock, remember now you have 8 black socks in your drawer, so it would be 8 out of 12. Multiply across, and that would be 32 over 144. So this is an independent event because me picking out the white sock didn't impact me picking out the black sock next because I put the first sock back. All right, let's try number 2. Calculate the probability of reaching in twice for a sock and first selecting a black sock and then selecting another black sock. Assume you didn't put the first sock back in the drawer. All right, so if I look at my sock drawer, which I have over here, right, you have 12 socks. The first black sock you pick, you had 8 of them to pick from. Now, you didn't put the sock back. So remember, you picked a black sock. So I'm actually going to eliminate black from my drawer. How many socks do you have in your drawer now? And you should say 11. Now, if you're picking another black sock, how many black socks do you have left? Well, remember, you took a black sock out, so he was eliminated. So he's not in the drawer anymore. That means you have 7 left to pick from, and that's why the second probability is 7 out of 11. And that's an example of me adjusting my probability of the second event because the first event impacted it, which is why these are dependent events here. This guy was dependent on this one happening first. That would be 56 over, I believe that's 132. I'm just double checking my math there. Yep, 132. All right, and that concludes categorical data. Moving on to quantitative data. We describe quantitative data using mean, median, mode, and standard deviation. Mean in your calculator is the X bar symbol, and that's just the average of your data. Median is the middle value. Mode is the data value that appears most often. And standard deviation, which is this little upside down baseball cap looking thingy, is just how spread out your data will be from the mean or center. So, given this data set, I want to find the mean, median, mode, and standard deviation and round to the nearest hundredth where necessary. So, you're going to see me take this table, call the left L1, the right L2, and plug it in my calculator. So in order to do this, I'm hitting Stat, Edit. Let me clear out my old data here. So I'm going to highlight the top, hit Clear, and Enter. So I've got 18, 17, 16, and then the frequency is 2, 11, and, oops, 12. All right, so ages of 25 students in a math class. Now I hit Stat, Calc, and then I'm going to pick one var stat. Now, if this was empty for you, so I'll actually show you, you'll have to fill that in because you do have a frequency list. So if this is empty, highlight over it and hit second option 2 because that will tell the calculator to make sure they check L2 for a frequency list. And then I'll hit Calculate. So the first thing you're seeing is X bar, which is the mean, which is 16.6. The median, I have to scroll down for slightly. He'll say med. There we go. Med is 17, so that's your middle number. Now the mode is not from the calculator, it's just from the list. What age happened most often? I have 12 of the 16-year-olds, so that means 16 years is the mode. Lastly is the standard deviation. Okay, go back to my list. To the nearest hundredth where necessary, it looks like it's 0.63. And then you're done. Z-scores tell you how many standard deviations you are from the mean. So here's your formula for it. Now keep in mind, in a standard normal distribution, your mean is 0, standard deviation is 1. So each of these little things that I'm listing on the x-axis here are representing z-scores. If you have a z-score of 1, you are 1 standard deviation above the mean. If you have a z-score of -2, that means you are 2 standard deviations below the mean, and so on and so forth. So everything there you're seeing are z-scores. So on the SAT, the mean math score was a 525. So mean math score was a 525 with a standard deviation of 25. Bridget scored a 500. What was her z-score? AKA, how many standard deviations above the mean was she? So it is her score minus the mean, so mean was 525, divided by a standard deviation of 25. So if I pull up my calculator, I can do 500 minus 525 and get -25, which then divided by 25 would be a -1. So that means she was performing 1 standard deviation below the mean, which means she's like there. So this leads me on to then normal distribution questions. In order to answer a normal distribution question, I always recommend drawing a picture and shade the area that you're trying to find. And whenever we're trying to find an area, that's when we're using normal CDF. So the scores on the most recent Algebra 2 test were normally distributed with a mean of 75% and a standard deviation of 3%. Find the probability a score is less than 70 and round to the nearest thousandth. So if I draw a normal distribution curve, again, the mean of my distribution would be the middle, so 75. Here's a 70. I want to find the score that is less than 70. So I'm shading the area to the left of that value. That's the area I'm trying to find. So using normal CDF, my low bound would be -1e99 for negative infinity. My upper bound would be 70. The mean is 75, and the standard deviation is 3. And it will prompt you with that in the calculator. Okay? At least it should, unless you're using a calculator that isn't updated. But I think we got most of you guys with 84s that will prompt you. So second var is option 2. I'm plugging in -1e, which is at second comma, 99 for negative infinity. Oops, let me throw another 9 up there, although I think that would still work. My upper bound was 70. Mean is 73. Standard deviation is 3. Oops, I'm sorry, mean is 75. Hit enter to get to paste. Notice how that matches the work that I showed, and this is me showing my calculator work. Hit enter, and to the nearest thousandth, we get 0.048. So you're thinking about 5% of your data would be less than getting a 70 on the test. All right, now what if we want to go in the opposite value, or the opposite direction? This is where we would use something called inverse norm. Now, keep in mind that we also talked in this unit about something called percentiles, which just tells you what percent of people you score better than or equal to. So, for example, if you scored in the 85th percentile, then you scored better than or equal to 85% of the students taking the same test. Now, with these inverse norm problems, we'll typically give you a percentile rank, which means you actually know the area to the left. So for instance, if you know you're in the 85th percentile, that means the area to the left on a normal distribution curve would be 0.85. So going over to my problem, on the last trig test, the mean score was an 84 and the standard deviation was 3. The scores were roughly normally distributed. What test score represents the 90th percentile and round to the nearest tenth? So if I were to draw a picture here, mean is the middle, so 84 is the middle of my distribution. Standard deviation is 3. The 90th percentile would be somewhere over here because that means the area to the left would be 90% of the distribution. Now keep in mind the area under the entire curve is in terms of 1.0, so that means your area to the left is 0.9. So again, I know the area, which means I'm going to find the value that gets me that area, and that's where we use inverse norm. And that's second var is option 3. It'll prompt you to ask the area to the left. The mean is 84 and the standard deviation is 3. So second var is option 3. Now if you have a newer calculator, it might be prompting you with something like tail and it says left, center, right. Just always keep it at left because it's the area to the left of that value. So here we go. I plug in the 0.9. I plug in the 84. Oops. I wrote 54, 84. I plug in the 3. And then I will hit paste. Rounding to the nearest tenth, it looks like an 87.8. So that means on this particular test, if you were to score better than 90% of the same people, 90% of the people who took the same test, you would need to score an 87.8. And I believe that's the end of Unit 13. Okay, so this concludes the end of Unit 13, which then means the next section will be summarizing Unit 14. All right, so I added a cute little header for myself. This is where it divides. All right, so here we go into statistics. A lot of writing on the paper, so I always recommend like highlighting important information as you go. First of all, population versus sample. Make sure you guys understand that the population is your entire set that you're trying to get information about. The sample is who you take from the population with random sampling to then help you make inferences about the population. So a cereal processing plant receives a truckload of Fruit Loops. Fun. The quality control team randomly chooses 3 pallets of Fruit Loops, each containing 36 boxes from the truckload. Identify the sample and the population in our given scenario. All right, so again, let me go back to the beginning. A cereal processing plant receives a truckload of Fruit Loops. So we get a truckload of Fruit Loops. Quality control goes onto the truck and selects 3 pallets from the truck. So what you should be figuring out is that the truckload is the larger amount. The pallets are the smaller things coming from that larger amount. So sample would be your 3 pallets from that truck. And you could say your 3 pallets including 36 boxes. That's just extra info. The population was the truckload of Fruit Loops. All right. So next, observational study versus experiment versus survey. For an observational study, participants are randomly selected. They are observed only with no intervention, and it allows us to describe a population. Experiments, your people could be randomly selected, but there has to be random assignment taking place into 2 groups, at least 2 groups for comparison. Subjects are acted upon with some sort of intervention, whether it be a placebo, a treatment, a control, and it allows us to conclude cause and effect. So I'm going to put a star next to this. Experiments are the only way for us to conclude cause and effect, which, oh my God, look at that. I actually included it with a star down below. Lastly, in this section, a survey is a specific type of study that gathers data by asking people for their responses to questions. This is technically neither observational study nor experiment. You're just asking questions and gathering data. All right, so I would recommend you to pause this and try the next 3 multiple choice yourself. Otherwise, I'm just going to go through and do them. So first guy, you got 20 students that were randomly assigned to take a paper test. Another 20 were randomly assigned to take an online test. Mean score of the two groups were compared. As soon as I see random assignment into two groups with a treatment, I'm thinking that's an experiment. 13 shoppers bought the more expensive brand of laundry detergent. Another 13 bought the discount brand. When they sent back their opinions on detergent effectiveness, it was concluded that the discount brand was far more effective at cleaning white clothing items. Now, although you're seeing apparently two groups of people making like different purchases, there's no sort of treatment imposed here, and people are responding on their opinions. So this is looking more like a survey. Okay. So lastly, 32 patient files were selected at random. So selected at random from a doctor's offices, and their cholesterol levels were recorded. So from your 32 patient files, that's your sample. Since we're just randomly selecting, we're not doing anything to these 32 patients. We're simply collecting data to help us make inferences about those doctor's offices patients. This would be an observational study. So I keep mentioning random assignment, random selection, and so on and so forth. What does that mean? Remember, random assignment is actually very strategic, and you could employ methods of using random number generators, random number tables, or even just flipping a coin. Hey, I flip heads, you're in this group. Hey, I flip tails, you're in this group, and so on and so forth. So the big idea is that you need to assign each subject a specific number and employ one of the above methods. Make sure you skip any repeat numbers, ignore spaces, and continue on to the next line. So given 50 volunteers, you must select 5. Each volunteer is assigned a number 1 through 50. So I'm just going to start at the beginning here since it didn't tell me to start anywhere else. And since I'm doing 2 digits for each person because there's 50 total people, I'm going to zoom in here. I'm going to block off 2 digits each time, skipping any spaces. And I like to give myself a decent amount to work with before I go back to the beginning, because sometimes I feel like marking this off can be one of the more tedious tasks. Okay, so if I go through, I figure out who's in this interval, because that was a number I assigned, and who's out. So like 61 doesn't represent a person, so I'm going to ignore him. 42's in the interval though, so that's good. Oop, I got 42 again, repeat, so ignore. Can't pick the same person twice. 4 is in, 19 is in, 86 is out, 54 is out, 60 is out, 5 is in, and lastly 17 is in, and that's my 1, 2, 3, 4, 5 volunteers, and then you're done. And I randomly selected them. It's random because everybody had a number that was different, and everybody had a chance of getting selected. It was just whatever the numbers spoke to do. It was fate. It was randomness. Okay. Where did my notes go? Oh, I found them. Okay. Whew. Next is sampling variability. So sampling distributions happen when you gather multiple samples from the same population. So think about that baseball problem that we did back in Unit 14 where everybody drafted their little teams of 10 and they looked at their throwing distances. Everybody got different samples, which is what makes up sampling variability. You're just going to have different statistics with repeated sampling. We also discussed that as sample size increased, standard deviation or spread and therefore variability would decrease. So what you guys are looking at below are 2 sampling distributions of the proportion of orange candies in Reese's Pieces, and I used my Rossmann Chance simulator from class to generate this data. The first guy has a sample size of 10, and the second guy has a sample size of 50. I increased sample size, now compare your standard deviation. It went from 0.156 to 0.069. So because sample size increased, standard deviation decreased, and your data gets tighter around the center of your distribution. That leads us into something called margin of error. So with standard deviation decreasing, margin of error would decrease as well. Margin of error is just your 2 standard deviations above and below the mean. So that's what I just drew in on that normal distribution curve. So you can also figure it out if I give you like a middle 95% or a reasonable interval, and you would do high minus low divided by 2. With your highest value being right here at the upper end of your 95%, and your lowest being down here at the end of your middle 95%. All right, so the heights of male students at a college are approximately normally distributed. Within this curve, 95% of the heights are centered about the mean, are between 62 inches and 78. So there's your 95, there's your low, there's your high. To figure out the margin of error, I'm going to do high minus low divided by 2. The high end of my middle 95 was 78. The low end is 62. And then I divide by 2. And I get 8. So what would the standard deviation be? Well, I know 2 times the standard deviation equals the margin of error, and I just found the margin of error is 8, so that means the standard deviation must be 4. Now, what if I want you to find the middle 95%? It is always going to equal whatever my observed mean is plus or minus 2 times the standard deviation, or my observed mean of sample proportions plus or minus 2 times the standard deviations. So, in this picture over here on the right, I think I have 100 dots, I don't even tell you, but I do give you a mean and standard deviation of this sampling distribution. I want to determine the middle 95% of the data above. You're simply going to use this distribution, this data, and do mean plus or minus 2 times the standard deviation. So 0.504 plus or minus 2 times 0.069. Grab your calculator. All right, so that would be my low end of the distribution. I'm going to go ahead and copy, paste. Oops. Make this a plus. And that would be my high end. So 0.366 to 0.642. Now, something like this on a Regents, they tend to throw in a rounding direction, in my opinion, just to like find a way to try to trip you up. So just make sure you read, because they could put nearest hundredth on this, and I'd hate for you to lose a point for rounding. So just make sure you're aware. I feel like they tend to have you round to the nearest hundredth, so that would be 0.37 and 0.64, so just be aware of that. Now, again, what this means is this is the reasonable interval for whatever population you're looking at. So middle 95% of your data that you're looking at here would be about like from there to there. Oops, maybe a little bit too far. Which throws out that outside 5% from your middle 95. Now remember, anything outside of that interval is considered an unusual or rare event. So like this 0.72 would be considered rare. This 0.32 would be considered rare or unusual. It does not happen very often based on random chance alone. Everything in the middle 95% is considered usual or expected. So I know the bottom of this distribution says proportion of orange, but I'm just going to pretend it says proportion of heads for flipping a coin, which honestly would make sense because look at the mean, it's at about 0.5. What this means is that it is reasonable to expect that a fair coin, when you flip it, however many times in the sample, I would have to give you more info, it's reasonable to expect that you would get between 0.366 or 36% heads or 37% heads and 64% heads. it would be unexpected when flipping a coin for you to get something like 75 or 72 or even 80% heads, because that falls outside of your middle 95, okay? 60%, totally fair. In your middle 95, that would be expected. So typically this is asked in a question on the Regents. I mean, they do a bunch of different things, but usually it's Melissa flipped her coin and she got 0.8 as, or let me put it this way, she flipped her coin 100 times and got 80 heads, which would be a p hat of 0.8. Do you think her coin is fair? So you would compare her p hat of 0.8 to this distribution of a normal or fair coin, and you'd be like, well, 0.8 is like way out here. It's way outside where the middle 95 is. That's unexpected for a fair coin. Therefore, it causes you to question that Melissa's coin is fair. So that's how that's expected. Now, if you're watching this video in 2022, we accidentally didn't include difference of two means, so just be aware that this section is supposed to be in your notes, so you're going to want to take a couple notes on this topic. If you're watching it in the future from when I'm making this, hey, what's the future like? And also you should have it in your notes at this point. All right, so difference of two means all has to do with running an experiment and comparing your difference between your treatment group and your control group. You're going to have a difference. It's just, is your difference statistically significant? Is it a big enough difference that it occurring would happen so rare based on random chance alone that something must be causing that to occur? So if the mean of a simulated group difference of means is 0.030, so we've got a group mean difference of that, and the standard deviation is 1.548, is an experimental difference of 5 statistically significant? So what I do is take my mean, add or subtract the 2 times the standard deviation, and come up with my middle 95. All right, and then I'm going to do the same thing, but with a positive. Oh, shoot, come back. All right, so we're getting negative 3.066 as my low bound, and my high bound is 3.126. So for whatever my data was, maybe it was differences in weights of tomatoes like we did in class, where I had my 10 tomatoes and I put them into one group and they got a treatment and the other group was my control, and I want to see if my treatment group grew bigger tomatoes than my control. I came up with a randomized distribution of the differences of their weights, and I figured out what's expected for randomness alone to get my middle 95. Now, if your experimental difference to start was 5, which is outside of that middle 95 of what's expected, that would be rare for that to happen based on random chance alone in my one experimental trial. So what that's telling me is something must be causing that difference of 5 to happen. So because that is outside our middle 95%, or it's occurring less than 5% of the time, that causes me to say, oh, 5 is statistically significant, so that the treatment must be causing that to happen. So answering the question, is this statistically significant? Yes, it's statistically significant because it falls outside middle 95%, or I'll even say it occurs less than 5% of the time. I'll just leave it as less than 5%. Okay, now if you need to revisit more specifically what difference of means means, I'm going to recommend you go back to our Algebra 2 directory and watch the day 7 notes video for Unit 14 if you need a more thorough explanation of difference of means with the tomatoes. And that concludes our Unit 13 probability and stats notes. Whew! 40 minutes. I honestly didn't think I could do it in that short of time. I thought it was going to take me at least 50.